Now we're going to move away from hardware a little bit, and we're going to move more into the completely software domain. And we're going to be talking about two different kinds of optimization tools. The first is talking about CVXPY, which is a set of optimization tools that Stephen Boyd's group has been working on, and it's been widely deployed. And Parth will be giving an overview of the tool. Go ahead, Parth.
All right, let me make sure I actually know how to click the slides. Great, I can go that. Do I have a laser pointer? Maybe not. OK. Hello all. I'm Parth Nobel. I'm a PhD candidate here at Stanford in electrical engineering. I'm also a core developer for CVXPY, a large open source project. We have over 500,000 downloads every month, and we're widely deployed across industry. So just this week, I got an email from one of the largest utilities in France, telling us about how they were using our project and thanking us for implementing a new feature that they'd been waiting for. So it's cool to be working on something that people are out there using. So let's learn out a bit more about it. So before we get started, we're going to just talk about what is optimization, and we're going to just kind of understand the problem. Most of you are probably used to hearing people talk about optimization, and they're going to say, we have all this data, and we're going to optimize the weights of this neural network in order to make these predictions. And they have a great time with that, and they do that off. But we're going to look at this in a bit more mathematical framework. And so we've got, here's a generic optimization problem. We're picking the values of a vector, right? In a neural network, that'd be your model weights. In a hardware design problem, you might be picking the widths of your wires in order to make sure that your clock speed is appropriate. Then we have an objective function that is minimized. And so maybe we're trying to have as thin of wires as possible to lower power consumption. So we're going to so we want to have an objective function that is going to be some function of the widths of the variables we're deciding. Then we have our inequality constraint functions that are going to be maybe we have a budget. We can only fit so much area on this chip, right? So we're going to say, well, if the wires are too thick or too wide, then they're not all going to fit. So we have to sum them and make sure that they are narrow enough that they all fit into the space. And we have some equality constraints. We have to have connections between different nodes, something like that. And the idea is we have all these functions, and we can really describe almost any interesting problem as an optimization problem. Whether that's a useful description is another question, but anything can be described this way, right? You can always set the objective to 0 and then just turn it into a constraint problem, right? But we're going to focus on a particular special case. But first, this is useful in control. Lots of control systems are designed this way. We'll do an example of that soon. It's useful in machine learning and statistics, as I mentioned with the neural networks. Finance uses this in order to design portfolios. They'll say, we want to bound our risk. We want to make sure we get as much returns as possible. And using a model that they're building, they'll then design their portfolios. The supply chain, I've frequently spoken with Amazon about how they use these types of optimization models to decide how to schedule what packages go where, for example, which is a surprisingly difficult problem when you're at their scale. And we'll talk more. We can talk more about the others later. So what is a convex optimization problem? CVXPY only supports convex optimization, so what makes things convex? Well, the first idea is that now we're not just going to allow any function. So now we actually have some restrictions, and not every problem can be written as a convex optimization problem, but most interesting ones can. And the idea is we're going to have some objective function, which is going to be convex, and we're going to have our inequality constraints be convex. And we'll discuss what that means in a second. And then we're going to have linear equality constraints. So we might say that all of our variables have to sum to 1. If we're investing in a portfolio, we have to make sure that we're putting all of our money into the market, and we're not. And so we'll have equality constraints on ensuring that things sum up correctly. But for the inequality and the objectives, we're going to let them just be any convex function. So here's 3 convex functions, right? We have the absolute value of x, which is a non-differentiable convex function, right? It's not differentiable at 0. But that's a convex function because it curves upwards. The idea of convexity is things are curving upwards. Then we have another one, the red one, which is going to be x squared, which is probably it's got an upward curve, not too complicated. It's nice and differentiable. And then probably my favorite convex function, we just have the line. It's just the line, still convex. It doesn't have any curvature, but that means it's still curved upwards in our definition, right? So that's our 3 convex functions to kind of give you a sense of what we can impose. OK, so now the question is, how do you actually solve an optimization problem? And if you go over to the people who do work on neural networks, they'll tell you there's this thing called gradient descent, and it works for everything, and you don't have to worry about any details. But it turns out that's not quite true. They spend all their time adjusting learning parameters and worrying about like how everything behaves, and we'd like to do better than that. We want to be able to just write a model down, not worry about how we're solving it, and give you a nice, accurate solution that we guarantee is correct. And so the classical view of when are things easy and hard just splits things into linear and nonlinear, and asks the question, if we have a linear objective and linear constraints, then it's easy. And this is called linear programming. It's probably quite famous. Some of you probably have had to work out simplex by hand during some class in Yushook college. I'm so sorry. But the key is that's actually that's not true. The research over the last 20, 30 years has really developed this rich theory of how to solve any convex optimization problem. These are highly nonlinear, sometimes non-differentiable, and still works surprisingly well and are surprisingly good. We can solve them with surprising amounts of accuracy. And so this is kind of the idea. We want to have convex problems, not necessarily linear problems. We can do, and linear problems are, of course, convex. All right, so how do you actually solve a convex optimization problem? So I'm not going to bore you too much with the details, but there's a lot of different algorithms. Some of the best, most highest quality ones are called interior point methods. And those are accurate, incredibly high accuracy, and they scale well for problems with tens of thousands of variables, tens of thousands of decision variables. If you're used to training giant neural networks, that's obviously quite small. But so then we get into, and convex optimization problems can get larger. We tend to use what are called first-order methods, where you just look at information about the gradients or things related to the gradients to understand the first-order methods. And so those work for very large problems. That's kind of the stuff that Amazon would use for scheduling their entire supply chain, would be kind of first-order methods, oftentimes distributed across many, many servers. Turns out they have a giant cloud infrastructure at Amazon that they're allowed to use for this stuff. I was a bit of a surprise. And what's really cool about almost all these algorithms is they don't require much babysitting. I'm not going to spend my time worrying about how accurate my solution is going to be based off what learning parameters I pick. It turns out that I can dynamically just kind of look at the results as they go in order to pick the hyperparameters and do a very good job of having these kind of model-free kind of, I just put my model in and it'll automatically solve it without me having to spend all my time fiddling with little knobs. And for the vast majority of problems, that's the case. And so that's really awesome, and means that you get to really focus on how to model your problem and not how to solve your problem, which is, I think, a very powerful tool. And so CVXPY is a modeling language that is designed to help you quickly write down a problem in an interesting way and be able to actually test and deploy it. And that's kind of our idea and our promise. And our solvers can be very reliable. If you ask me to, I can write a solver for you that guarantees that it will have no division by zeros in the entire execution path. We are able to guarantee that there will not be a single division by zero in the entire execution path, which is great, which is why SpaceX, probably our most famous user, uses this in the control system for the Falcon 9 rocket and the Falcon Heavy rocket. And so when you've probably seen the famous video of a rocket landing on a barge, the actual decision of where should the rocket be going and targeting this moving platform is all done with convex optimization. All right. So what's the idea? You take your problem, you write down something interesting about what you're trying to do, you try and write it as a convex problem, and if you succeed, we can solve it for you. And so, yeah. So there's some tricks as to how to do this. It can often help to reparameterize your problem so that you write it in terms of different variables. It can often help to approximate things. You know, people will say, I want as few of these to be non-zero as possible. And we can say, well, what if we just promise that their absolute values are small? Maybe we don't actually need to minimize what's called the L0 norm, the number of non-zero entries. We can just minimize what's called the L1 norm, the sum of the absolute values. And that'll probably work just as well for most applications. And that's what they do in statistics. It's called the lasso, where when you want to have pick your features, you apply what's called L1 regularization, and you get what's called the lasso. And it works very well for kind of selecting only the features that appear to be relevant to what you're trying to solve. And then also, the most powerful tool is called relaxation, where you just ignore things that you can't handle. It works shockingly well. Most of the time, you can add it back later. But yeah, there's in New South Wales, there's a giant battery facility that has to, it has to fill it's powered by this giant solar farm. It fills up all the batteries, and then during the night, it powers the entire grid by letting power out of the batteries, right? Well, they do all of the scheduling of when do we fill, when do we discharge, based off of convex optimization using CVXPY. They have Raspberry Pis in each battery rack, and they're all running CVXPY. It's surprisingly straightforward off-the-shelf hardware. But there's a problem, which is that the regulators only give them subsidies if they're helping the grid by pushing enough power out, or they have to charge up to over 80% every day, and they have to discharge to below 20% every day, or they don't get their regulatory subsidy. So it turns out that's not a convex constraint. So what they do is they do a relaxation where they just totally ignore this non-convex constraint. And they just schedule when should we charge, when should we charge, when should we discharge, based off weather predictions, et cetera, right? Then they just go in, they find the time where they're going to have the most capacity, and they find the time where they're going to have the lowest capacity, and they just say those have to be above 80 and less than 20. That's a convex constraint once you fix the time, and you don't have to pick what time it is. And then they just reschedule based with these new constraints. And that works perfectly for giving them a quite good schedule that makes them money, that helps stabilize the power grid, allows solar power to be used full day round, which is great for all of us. And you know what? The relaxation works perfectly. You just ignore the constraint, and then you add it back later. All right, so CVXPY. What is CVXPY? I've told you about convex optimization. I've told you about some of our customers, or not customers, but some of our users. So we're a domain-specific language for convex optimization. It's a way for you to write a convex optimization problem so that we will translate it into solvers. So the solvers tend to be written by some very, very good people, both here at Stanford and Oxford, and at a small startup or I guess now it's not a startup, but it's a small company based out of Denmark, are probably the three best solvers are from one of those three locations. And those solvers are written for math people by math people without really thinking about how users are going to interact with them. We spend all our time thinking about how people who don't know a bunch of theory are actually going to interact with the solvers. And so we let you describe things as math. You do a quick, rapid prototype, and then you can quickly deploy things. And I cannot understate how short the code gets most of the time. And here's the basic idea is you say what you want, not how you're going to get it, right? So yeah, we've been around since 2014. I'll skip this. OK, here is my first CVXPY example. On the left, you have a constrained least squares problem, right? You want to do non-negative least squares. So all of you're trying to fit data ax equals b, or ax minus, right? We're trying to fit our data ax and b. But we think for some modeling reason, we think all of the x's should be positive or non-negative, right? So here's our definition. We declare that we're going to have a variable of a size n. We're going to say that our objective is ax minus b squared. We're going to have a constraint that x is greater than or equal to 0. And then we're going to minimize the objective subject to the constraints. And now we're going to solve it. It's basically, I just take the math I wrote on the left, and I type it up into code. And CVXPY will automatically convert that to a form a solver can solve and find the solution, which is very, very nice for, it makes my life easier when I actually want to fit statistical models and I want to toy around with how we're modeling things, is I can quickly iterate and change it. I can add a regularization term if I want to add some more other terms, and it's quick and easy to work with. So how does CVXPY tell if functions are convex? So it turns out that this is, if you go to the theorists, they tell you that studying a function and telling whether it's convex is NP hard and yada, 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 yada. It's actually, I think, in P space, not even NP hard, so it's a whole nightmare. And so it's quite difficult. But it turns out, in CVXPY, we give you a trade-off, right? Somebody said that there's no free lunch in one of their talks previously. And so we also don't give you a free lunch. We say you can restrict, if you're willing to really restrict how you write down your functions, we can guarantee it's convex, and we can do the kinds of transformations we need to be able to make our stuff work. And so we have one rule, which is that a function whose arguments follow certain behavior. If that function is overall convex, and with its arguments, it will remain convex. I won't bore you too much with this. 9 times out of 10, you don't even notice this rule, but this is the one rule that we apply to everything and works surprisingly well. But that's kind of the theory of it. And so every once in a while, somebody comes to us, they show up in the CVXPY support forums, and they write out something, and they're like, I can't get this to be convex. And we always find this to be a fun challenge. Normally, one of us gets it pretty quickly. And if no one can get it after a little bit, we start forwarding it around. And there's this professor I believe he's in the UK now, named Nestorov, Yuri Nestorov, who you just, if none of us can solve it, you just email him. And you say, hey, how would you do this? And so it's called a Nestorov hard function. If Yuri Nestorov replies with, I'm not sure. And I have never encountered a Nestorov hard function in my career, but I'm told that like 3 of them exist, and they're all very carefully documented somewhere. And so, all right. So now we're going to do a quick application. We're going to look at Kalman filters, and we're going to make a Kalman filter that's robust to noise. And so here's the basic idea. We have a movie vehicle. We have noisy measurements of the behavior of our vehicle. We want to understand what's going to happen as we move along, right? All right, so I'm going to make the completely absurd assumption that our vehicle follows linear time invariant dynamics. If you believe that, I have a bridge to sell you in New Jersey. But if you think it's a good modeling assumption, that actually probably is. It probably is. And so the basic idea of a Kalman filter is you solve this optimization problem. This particular optimization problem has a closed form solution that I'm sure a few of you have been unlucky enough to derive during some class and controls class when you were younger. And the basic idea of it is this has been widely used since the 1960s, and it's easy to work with. All right. So the Kalman filter, so we're just going to write this out in CVXPY, and it's nice and simple. But this is where things get interesting. The Kalman filter works really well when the process noise and the measurement noise are both Gaussian. That's not very realistic. If you have it's possible that what's going to happen is somebody's going to bump one of your sensors, right? If you have a passenger in a vehicle, maybe they're going to accidentally wave their arm out and hit a sensor, and that sensor is going to have a sudden spike, and it's going to have this insane outlier behavior. And it's not going to look Gaussian. It's going to be more common than that, and maybe you're going to pass by a pole too close, and the model that's predicting things based off a camera is going to really get confused. So we want to make things robust to occasional outliers that are going to be very large and very much an outlier. And so how do we do that? Well, we use something called, we're going to just modify the problem slightly. We're now, instead of looking at the squared loss in the objective of the noise inputs, we're going to be looking at, of our model of the noise, we're just going to be using what's called the Huber loss function, which here it's plotted in blue. In red, we have the square. In blue, we have Huber. And the basic idea is, instead of growing faster, once we get past some threshold, in this case 1, we just have a linear growth instead of a square quadratic growth. And so that makes sure that while we're still encouraging things to be small and shrinking them towards 0, we're not growing too fast when we have a big outlier. So you don't start over-worrying about a couple of small outliers. So here's the code in CVXPY. You'll notice I changed exactly one line. Line 6 got changed from having a square there to a Huber. And otherwise, it's more or less exactly the same. And that's kind of our easy to write, easy to read promise. And it works shockingly well, right? Here's our data. Our blue, all the blue measurement points are the measurements you get over time. The true trajectory of the vehicle is the green line. The robust Kalman filter follows it closely on the red line. And the original Kalman filter gets distracted by all these outliers and ends up having these huge deviations from the green line. So it worked quite well at being able to correct it. All right, that's about it. Promise is, convex optimization is a powerful tool. It's used widely. CVXPY makes it easy to prototype. Anytime you find yourself trying to find the best of something or trying to model something or fit data, it can work amazingly well. It scales well. It's used in production by many people. It's all open source. Every piece of the entire stack is open source, and it's available at cvxpy.org. And if you want to learn more about convex optimization, there's a great textbook by Stephen Boyd and Lieven Vandenberg. There's a class, E364A, that Stephen and I spent the summer redesigning. And we have a lot of software in other languages as well. So if you don't use Python, we have Julia, MATLAB, and R as well, versions of CVXPY. And we also have a short course that takes about 8 hours to run and is available. All the resources for it are available online. All right, thank you very much.
Questions? Any questions? Oh, got to get, yeah, go ahead.
Yeah.
So you said you had to show that the functions were actually convex. Why do you need that?
So we need that because we're doing a transformation from how you describe your problem to how the solver will solve the problem. And so the way that transformation works is, I don't know how much of convex analysis you know, but we change it from this functional form that's easy to read to what's called a conic form, where we describe how the function's behavior involves basically vectors lying inside of very strangely shaped cones in very high dimensions. And so the conic form, in order to do that transformation, we actually need information about the structure of the function, which we get from you complying with our rules. So there has been talk about trying to do an extent. There are extension libraries called NCVX that allow you to not require convexity, but they kind of change how you have to write your problem a bit. But yeah, we do have an extension library called NCVX that does cover non-convex, some cases of non-convex optimization.
Are there other questions? If not, I have one question.
Yeah.
So you said there are various companies that sell solvers. Does CVX have its own set of solvers that are open domain?
Yes. So Stephen Boyd's group here at Stanford has developed 4 or 5 solvers at this point that are all open source that we ship with CVXPY. Most recently, we've actually been switching to a solver being developed by a team at Oxford, Paul Goulart, if anyone knows control theorists. His group has been developing a phenomenally good solver called Clarabelle that we are switching to right now as kind of our default. But yeah, we have lots of open source solvers. There's maybe 3 or 4 companies that sell very good proprietary solvers, but frankly, the Paul Goulart's group at Oxford is really giving them a run for their money. And it's harder and harder to recommend a commercial solver over the open source ones at this point.
I see. So in my experience, and not in Convex, I don't know anything, but generally, different solvers are useful, or they shine in different classes of problems. Does CVXPY sort of analyze the problem a little bit and ship it to the right kind of solver? Is that what happens internally?
Yes, exactly. Yeah, we detect how much complexity we need to describe the problem, and then we send it to the solver, which has the least, or which is most carefully tailored to that application. Though interestingly, Paul has some benchmarks suggesting that Clarabelle is actually just better than everyone on everything. I'm a little skeptical of all of the numerical results, but we're hoping to dig into it and see if that holds out to be true.
Okay. If there are no other questions, let's thank you again for your great talk.